Hello everyone, welcome to our Toronto Innovation Seminar. And today we are very honored to have Jinyang to give a talk. And before I introduce our speaker, I'd like to acknowledge our sponsor, Google DeepMind Field Institute and the Art and Science faculty. We will take a few pictures during the seminar. So if you don't want to be included, please let me know. Today we are very honored to hosting the Jinyang. He's a professor at University of Quebec. His research interests cover ultra-fast imaging, coded aperture imaging, optical physics, and biophotonics. He also received many awards, including the 2025 Zhutong High-Speed Imaging Achievement Award, the 2024 Early Career Investigator Award, and the 2019 Young Scientist Prize. So please join me in giving warm welcome to Jinyang.
The mic's over here, so it's good.
All right. Thank you, Dou-Yu, for this very nice introduction. Hello, everyone. Welcome to my talk. I would like to start by thanking David for inviting me. Honestly speaking, I'm a little bit nervous. Okay, so this is actually my first seminar in a CS department. Okay, so I consider myself optical engineer. Okay, so although I'm doing computational imaging, computational photography, this type of stuff, compared to what you guys are doing, I don't think my research is computational enough. Okay, so I actually tried to tailor my slides last night to hopefully present some information that's both complementary and also, related to what you guys are doing. So so I'm from English is the National Institute of Scientific Research, IRS, the title of my presentation today is Coded Streak Imaging Concept, Systems, and Applications. So just a little bit self-introduction, I guess. So I'm from INRS. Okay, INRS is one of the 10 universities in the University of Quebec systems. So we're a teeny tiny university, although we have the name institute, but we're a university. And the university is scattered in the province of Quebec, and we organize our university not with departments but with research centers. So each one has its own, theme of research, ranging from rural development all the way to biotechnology. And I am working at the Center of Energy Materials and Communication. The lab is at the south shore actually of Montreal. It's here. So my lab is called the Laboratory of Applied Computational Imaging, LACI. Okay, so we have two research missions. The first one is we use ultra-fast photonics and computational techniques to engineer new computational imaging devices. And the second one is we apply those systems devices to various applications ranging from materials science to manufacturing and to biomedicine. So in my lab, high-speed imaging is the current research focus. So we have many different systems that can give you really high imaging speed in 2D, 3D, and if you want to go to 5D, and many more. Okay. And today I'll be talking about just one research direction of our high-speed imaging research, area. And this one is called streak imaging. So the outline will start from the introduction of, basically what is streak imaging. So conventionally, how were people doing this, and what is good about it? What are the limitations? And then this will lead to my introduction of why coded streak imaging is very important. So after I introduce the concept, I will focus on some systems that we have been working on in the past few years. how does it work, I mean, what is the application, and a short summary will conclude the talk. Okay, so first let's take a look at two images to understand what do I mean by streaking, right? So what is streaking? So the first figure or image is basically showing, fast-moving cars on the highway, at either evening or at night, right? So you see that, well, because the cars are moving, right? So its spatial position at different times are different. So when you actually use a relatively long exposure time to take this photo, what you end up to seeing is the car's red tail light, right? Basically left this trail, right? So similarly here, people are being creative, right? So because everybody has done this, turn on your flashlight, right, at night, and trying to shake it. Right? So if the exposure time is long, then of course you can have some very creative artwork. Right? So in a simplest term, right? So if you have a light streak or light trail, and this one's called streak. So scientifically speaking, how can we understand this a little bit more, right? So say we have a dynamic scene right here, draw x, y, t, right, using a coordinate system, and we have 6 frames. If you pull out your iPhone and try to take out the image, this is what you get, right? So, well, you can still retain the information in x, y, but the temporal information is totally lost because the iPhone's image speed is too low, right? So what you have is an integrated image. Now, if you have some way to do streak imaging, then instead of all the frames stuck on top of each other, well, each one of them is actually separated. So this is why for streaking, we usually say that it's a technology that can convert time to space, right? So in this way, even if you just take a snapshot, you'll be able to retain x, y, and t information. Okay, so now we think that, okay, the streak imaging concept is intriguing at least. How can we realize that optically? There are many optical devices that you can use to do this, right? So depends on how fast you want to image, right? So if we're talking about 1,000 frames per second ish, right? The typical way is we use a rotating mirror. So I think in David's lab, this morning I saw 2 gavel mirrors, right? So in this way, if you have a time signal coming in, after it actually gets reflected by the gavel or polygon, the time information t will convert it to different angles, right? And then usually you have a collimation lens placed at focal distance away to convert the angle to space. So in this way, you have t to theta to x conversion, and this is how you can actually streak a time signal. So if you want to do it a bit faster, at the million frames per second level, you can still do it using this like rotating mirror type of concept. But since the mirror has to be turned much faster, instead of using this ginormous mirror, we can rely on the micro mirrors that you usually see in a spatial light modulator. Okay. So now, what if you want to do it even faster, right? At billion frames per second level, right? G FPS. Usually this mechanical rotation is not fast enough to support the required imaging speed. So there we rely on some specialized optoelectronic devices to provide this level of streaking capability. So here what I'm showing is a schematic of a streak camera. So I don't really want to get into details, but in a nutshell, it converts photons to electrons, and then you can pull the electrons by using a time varying voltage, and after that, it can be converted back to photons so that you can measure. Now, what if you say like, okay, even billion frames per second is not good for me. I want even faster. Right? So beyond tens of gigahertz, you are actually reaching the limit of electronic bandwidth. So if you want to do it even faster, then you have to rely on optical bandwidth. So usually this means that you need to start with a very short laser pulse and try to chirp it so that different time is associated with a specific wavelength, and you can probe the event using this one and using some dispersive element, for example, grating or a prism to separate the light. So this is how you can convert it. So you can see the same concept can be embodied by many different devices. Previously, people are doing this in kind of like a conventional way, right? So what do I mean by that? So for streak imaging, you can do it in the active mode, right? So like what I said, if you have a chirped pulse, you probe it, then, this means that you're using a specialized illumination to retain the time information. If you want to do it in passively, you can also do that, right? So then this means that you use a streak camera to record the temporal information. If you only care about time information in a point, then everything is very straightforward because if you do streaking, a point will become a line, right? So if the field of view is 1D, then it's still very straightforward because a line becomes a band like this one. However, things get tricky when you want to retain everything. Right? So what if I want to retain 2D spatial information at the same time and still want to retain the time, right? So in this case, you can see that if I draw two squares, those are basically two adjacent frames, right, at different time points, then you can see these are the overlap, right? So this means that in 2D case, conventional streak imaging doesn't really work because you have a mixture between space and time. So from the technical perspective, what we are trying to answer is this just one question: how to resolve the space-time mixture to record a 2D ultra-fast movie in just one shot. And this brings me to at least my solution, which is encoding. So I think, with this audience, encoding for computational imaging is definitely not a stranger. So usually we need to ask ourselves 4 questions, right? So why, where, what, and how? I sort of touched upon, this why question, right? Because, some conventional optoelectronic imaging approaches, they have some limitations, right? So then we have to use encoding to solve this. But, where, what, and how, right? So I want to use 2 examples to kind of like illustrate this point. So this is my data here, right? So try to move the mouse out this. So right. So you can see that, where to encode? This is actually encoded at the illumination side, right? So what to encode is basically stripes. Why? Because I think stripes are sensitive to the depth change. So you can rely on to calculate the phase difference to figure out the 3D. And how? I believe, if I remember correctly, you used a projector to do this, right? So this is one type. And if you look at this paper, and this is also from here, right? So this is a Kyros's paper. Here, instead of encoding it, from the illumination side, we're actually encoding it at the detection side. More particularly speaking, we're actually trying to program the exposure sequence of every single pixel of the camera to enhance the imaging capabilities, right? So you can encode many different things, right? You can do a Hadamard encoding, or here you can just try to change the exposure time for each pixel, so that what this one shows is that you can actually have the very dim object and very shiny object all showed up in the same image to, enhance the dynamic range, right? So hopefully, till this moment, I've convinced you that, well, first we do need to have encoding to help the computational imaging, and the encoding can happen in many different places in the imaging system. And we have many different optoelectronic devices to help us to do encoding. And what to decode depends on the specific goal, right, about imaging that we're trying to get. Okay, so by carrying this mindset, let me talk about how we implement encoding for streak imaging. So we still start from this dynamic scene, right? So the first thing that we want is that, okay, if we can do streaking and we can do encoding at the same time, After that, we can totally separate these temporal frames. Then we're good, right? So in this case, we'll have no problem to retain the spatial and the temporal information. So here, streak does its own thing, but I mean, if you think about a little bit further, I mean, the streak operation is actually continuous. So in order to have this so-called framing photography type of configuration, what the encoding should do is to actually break the time continuity, right? So that in this case, even if we're doing this in a kind of like continuous mode, frame to frame, they're not overlapping. And at the same time, I mean, what if the frames cannot be completely separated? Right? So in this case, we have two solutions. So either we have a streaked mask so that each frame is attached with a different prior information, or we use the same mask and streak everything together. So the idea here is that even if the two frames they're overlapped, because the mask that will attach to each frame, they are independent. This will provide us with the prior information to help us to extract the spatial temporal information, put it to the correct spatial and temporal voxel. Right? So after this, we have to do a compressed detection because the camera is limited, right? So either we use a 2D camera to just take a snapshot, or we can use just the point detector to record the time information. But regardless of what you are doing, you actually compressively record a 3D data cube to either a 2D or 1D result, and you rely on the reconstruction to retrieve the dynamic scene. So this I use the compressed photography. So in the following, I'll give you a few examples from our lab in the framing photography and compressed photography to see how we use a different optical imaging system to embody these ideas. Okay, so in framing photography, the example I would like to cover is called drone photography, diffraction-gated, real-time, ultra-high-speed photography. So this is the system. So I won't go into the detail of the lines, but what I want to highlight is we use a digital micromirror device on the Fourier plane of this coded 4F imaging system. So if you have worked with DMD or SLM, you know that these things can be regarded as 2D diffraction grading. Right? So when we talk about gradings, then you know that two most important things that's associated to a grading is that they have discrete diffraction orders, and then they have a diffraction center, right, that allows you to basically concentrate most of the light onto a single order. Now with the DMD, because it goes by either on or off, the added tilted angle actually means that this device is a blazed 2D diffraction gradient. So our idea is that, since the diffraction orders are discrete, can we actually move the diffraction center so that we can use the diffraction as a gating? Well, as I showed in this movie, we relied on the interframe transition between the two patterns. So this process happens in just a few microseconds. So if you basically record the intensity of different order, then you see that when we actually do the on to off transition, different diffraction order will be written up. So this means that we duplicate the information that we're trying to record to different diffraction orders, and then use the diffraction to slice them out. So after you put them together, then you end up by using this ordinary imaging system to achieve a 4.8 million frames per second imaging speed. So just very quickly, we use this one to image laser ablation of a biological sample. This real-time movie allows us to do some analysis about its damaged area rate and also speed. So later on, we took one step further. Right? So because the DMD is placed at the Fourier plan, then we can do lots of different encoding to try to bring in different contrast, right, to the system. So what we did is to basically, instead of having just like on-off pattern, we have a knife edge. So in this way, when you flip the pattern from on to off, instead of sensing the white field or intensity contrast, we can actually sense the phase gradient. So this allows us to use the system to see the Schlieren imaging. So here is the example of how the image is applied to see the laser-induced plasma and cavitation in a single shot. So now let's talk about the alternative architecture. So here I want to start by showing how a point detection-based imaging system would work. Okay, so essentially speaking, I'm going to talk about single pixel imaging. So for people here who do not have a very, deep understanding of this, simply put, single pixel imaging by name, right? It's just like you want to use a point detector to record a 2D information at least, okay? But then, very obviously, you have a dimension mismatch, right? You only have a point detector, but you want to see, X and Y. So how to do this? Common way is to use a spatial light modulator to project different patterns onto the scene as an interrogation. So each time, you have a dot product between the scene and the mask, and you integrate them as a number. So if you have a series of this measurement, you'll be able to use, the measurement matrix and the sensing matrix to retrieve the XY information. Okay. How about the coding, right? So again, here I'd like to use David's very famous Nature paper as an example to start the discussion. Right? So, this is the confocal non-line of sight imaging, right? So even though the mathematics, the image reconstruction to me is rather complicated, but from the encoding perspective, this one is relatively simple. Why? Because the laser is actually illuminated at just one point each time, right? So from the sensing perspective, you are essentially just doing one pixel at a time. So the sensing matrix is nothing but just an identity matrix. But using the same configuration, we don't really have to restrict ourselves in this one point at a time type of measurement, right? We can actually do many different encoding scheme. For example, Hartmar, sinusoidal, right? There's many different choices. Here, what I want to introduce is what we are doing in our lab, and this is called the cyclic S matrix. So you can see that, if we have the knowledge of the first row, all the rows will be able to deduce, right, by basically shift everything to the left by one. Well, you want to say, okay, is there anything special? What's good about it, right? But this links to my, question in the previous slides, like, okay, what to encode, right? Because we want to encode this for some interesting mathematical properties that it can bring, so that we can realize that optically. So if you basically take this row and do a 2D reshape, you'll get to this one, right? So that's basically your 7 by 5 matrix, so that this is a 2D mask you can apply to the scene. But if you look at the second one, okay, so instead of having a totally different new mask, what it gives you is basically here, right? So you can see that 1 and 2, they are just shifted by just 1 pixel. So this is called the mask tiling. In addition, if, let's say, we do this one by one, and we try to do a 2D reshape of the imagined bucket signal, and because we found out that, the mask, right, is just shifted by one. If the object has a limited spatial bandwidth, then the recorded bucket signal are very similar. So in this case, I mean, we could use this property to simply just do the interpolation instead of using the iterative based reconstruction. So this could give us a lightweight image reconstruction. So by using these two things optically, we built so-called single pixel imaging accelerated by swept aggregate pattern, so SPIXR. So we still use a DMD, but instead of using it to directly project the patterns one by one, we combine it with a polygonal mirror. So what this does is that, after the laser beam gets reflected, collimated, it's actually swept through the DMD surface. So each time, only a fraction of the DMD pattern is illuminated. And after that, everything comes back to the polygonal mirror again to descan, right? So that we have a stable field of view, but the patterns just looks like, streaking from left, in this case, right to left. And this allows us to improve the pattern projection rate by over 3 orders of magnitude. And this enables one of the fastest single pixel imaging nowadays. So this shows at 300 frames per second imaging speed, we can actually see how in this case, a light bulb was actually burned in real time. And if we want to push the imaging speed, we can go all the way up to 12,000 frames per second. And finally, because we're still using a DMD, we retain the programmable, aspect of the system, right? So that's why we have a very good flexibility to tune the imaging speed and frame size. So later on, we try to apply this system to biomedicine. So the specific application that we're targeting is, fever screening or in general temperature sensing. So here we focus on a particular part of our eyes called the inner canty. Okay, so inner canty is basically here, right? So it's basically the inner corner of human's eyes. So why this one is important is because, if you look closely, the inner canty is simply just the meat exposed or tissue exposed. You don't really have the skin to cover that. So this means that this area is known to have a sensitive correlation to the core body temperature. So in fact, it has been suggested that instead of doing the fever screening or temperature measurement over the entire human head, we should actually focus here so that there will be no false positive, so that people do not suffer unnecessary burdens, right? So if you are mistakenly diagnostic, right? We all know what happened during COVID era. Okay, but in order to do this, we have to do it right from some international standard. It says that you cannot just do one pixel measurement. It has to have at least 3 by 3, and each one needs to have at least 1 millimeters area. Okay. And also, they suggest that there are some preferences that you have to take. Okay. First one, we want to do it label-free, right? Obviously, you don't really want to add some labeling in your eyes, right? So it has to be non-contact and also passive. Okay, among all these technologies available, what can we actually have, right? So this is basically the standard or gold standard or mainstream, and it's done by using a thermal camera. Okay, so you can see that. From here it's kind of obvious that this inner canty area has shown a higher temperature. But one is that the sensitivity is not very high, and also the thermal camera, right, has a very low efficiency. Why do I mean that? So let's say we take a camera, let's say 500 by 500, right? So the number of pixels allocated to the inner canty is only less than 1%. So either you focus on this area, but you have to do it twice, or if you just want to take a snapshot, then it's just not very efficient. And also because you take everything, then I guess you can call it the background blending. So this means that if the focus is not very 100% accurate, then there's some background thermal energy will blend into the measurement. So this would reduce the accuracy. Okay. So by recognizing all these I guess importance and limitations, we propose to use the single pixel system to achieve this goal. So as you can see here, we're dealing with the thermal light, right, which is a far IR. So normally I guess a DMD or SLM, it doesn't work, right? So what we did is to carve or fabricate encoded masks, and we only had encoding specified in the two inner canty region. So in this way, the pixel assignment efficiency is 100%, right? At the same time, for a single pixel camera, we just need to have a very good cooling of a photodiode instead of a very complex cooling system for a thermal camera. So this allowed us to pinpoint the temperature distributions within the inner canty area of different human volunteers. So I actually found quite some interesting stuff, right? So if you look at this figure, so basically we measured about 40 volunteers, and each one of them, has different temperature, right? So left and right inner cantus, the temperature is different. And also, if we measure the temperature in the morning, kind of like late morning, early afternoon and late afternoon, you also see the cycles. So this is related to the physiological activities of human beings. And also, finally, very importantly, for all the volunteers, we actually detected one volunteer who just started to develop the fever. So, I know that the experiment was done during COVID. So at that time, it generated quite some nervous, at the center. But anyway, so this actually shows that even with this prototype, we have we have some I guess a promising result towards a single pixel based temperature sensing. So right now we are improving the system, because right now for this prototype, we have to ask people to open their eyes for 15 seconds. And there is lots of complaints and saying like, okay, this is not fast enough, it's not very comfortable. So we're trying to enhance the acquisition speed, hopefully by a factor of 50. And our final dream is to integrate the system to, let's say, a border security machine, where you have to take off your glasses and take the measurement, right, and take a picture. So hopefully, this one can be seamlessly integrated in that scenario. Okay. Now let's move on to I guess the last of my presentation. So here, what if we have a 2D camera, right, to help you to measure the transient delay? And the general framework works like this. Okay, so you have a XYT data cube, so it's kind of like a movie, and you image that to a spatial encoding unit, where you basically put a single mask to do encoding. So what this does is basically punches lots of holes, right, in the time direction. And after that, we have to have some unit that allows us to share the different frames according to their time of arrival. So this we call it temporal sharing. And after that, you just measure a time integrated image of the spatially encoded and temporally shared device. So this is why you start from the XYT data cube, and you end up with just an XY snapshot. And sometimes we also put a bit spinning here and trying to capture just the time integrated image. So in this case, well, because here you can see that the XY and the T, the information are preserved. But since we have to do encoding, then the some fine details will be missed. So here we totally throw away the temporal information, but we're trying to retain the spatial information as much as possible. So once we capture these two snapshots, send it into a image reconstruction algorithm. Old days we're trying to do this iterative reconstruction by solving the minimization problem. And nowadays, of course, we're also trying to use machine learning neural network to help us. So that's basically the general framework. And I've been working on this since I was a postdoc. So this is actually how my postdoc work stand out. So we've been using this to capture some fundamental light phenomena at record-setting speed. So that one shows the light refraction, right, at the air-resin interface. This one shows the spatial focusing and in splitting, capturing at 2.5 trillion frames per second. And then we also try to implement this in different scenarios to capture, plasma, photonic Marcon, or even spectrally resolved fluorescence mapping. So at IRS, we're also doing this, right? So in the next few slides, I would like to show we are actually able to cover many different imaging speed from thousands frames per second all the way to more than 100 trillion frames per second. So the first system is called the single-shot photoluminescence lifetime imaging thermometry split. So this is basically the structure that I just talked about, and we couple that with a wide field microscope. So here we're collaborating with a professor at IRS to image the photoluminescence of a rare earth of nanoparticles. So these things are interesting because it can absorb 2 photons at near infrared sequentially and emit at the visible, right? So either you want to image at the green band or the red band. But most importantly, what we see is that the emission lifetime is related to temperature, right? So it's called a Boltzmann coupling. So this means that we can capture the transient photoluminescence decay and relate it to the temperature. So by using this system, the biomedical application that we're targeting is we're trying to see if we can use the temperature as a biomarker for skin cancer early detection. So this figure shows that, previously people have already worked in this area. So what they found is that because, a cancer cells, right, take in lots of oxygens and nutrients, it has a higher metabolism, so generates more heat. So this means that the lesion area always have a higher temperature compared to the healthy tissue. Previously, people say like, okay, if the patient's melanoma is at that late stage, sure, we can. The device is capable of detecting it. However, a very important subgroup of melanoma is actually left out, and this one's called a micromelanoma. So by definition, micromelanoma is just small melanomas, right? So we're talking about the ones with a diameter less than 3 millimeters and depth less than, close to or less than 1 millimeter. So it's at a very early stage. But if you want to use the ABCDE criteria to see, okay, if this one can be detected, usually, it's not, because ABCDE stands for diameter, and the ABCDE criteria uses D larger than or equal to 6 millimeters. So this means that, it's kind of like an analogy, right? Here's a little bomb, but because it's too tiny, we think it's not very dangerous, which, doesn't make any sense, right? Okay, so we thought, okay, what is the mainstream? The mainstream is still the thermal cameras, but since they're using, mid or long infrared light, the wavelength is very long, the spatial resolution is very poor. So this means that it doesn't really have the ability to detect the micromelanoma. So we think this is a good opportunity, and we actually act on it. So in our very recent work, we developed this technology called smear. So our approach is to load up converting nanoparticles into a microneedle arrays. And we actually pinch this one into, let's say, a lesion area of, let's say, small animal, so that we can basically leave a luminescence tattoo on this animal. So we cool it down and use an optical streak camera system to watch the thermal recovery process. And what we found is that, well, because the tumor area has a higher metabolism, it has a higher recovery rate, and after it's recovered, the equilibrium temperature is also higher. So we are trying to be compatible with clinics. So well, I mean, honest opinion is that during the revision of the paper, people ask us to show a little bit more engineering maturity. So this is why we actually integrated with a robotic arm to show that we are able to move this system, in a very precise way to basically do the imaging with some, potential hype, right, to the future clinical translation. So what we showed, I guess this is basically the raw measurement to show the idea I just talked about. So there are a couple of, new technical capabilities that our system could bring onto the table. First, instead of having 5 millimeters or more detection capability, now we are using optical thermometry to push the minimum spatial resolution of temperature sensing to about 20 micrometer. And at the same time, since we are doing optical sensing, the temperature resolution is as low as 1.1 degrees. And finally, we're actually having this self-calibrated detection because, well, if let's say individuals they have different thermal responses, this is okay for us because we can always use a needle at the surrounding tissue as a reference to basically normalize the difference. So we think that the micromelanoma is now being taken care of. Okay, so this work is a collaboration between IRS and the two professors at the University of Montreal, and papers coming up soon. All right. So then next, I will just try to go through some engineering development relatively quickly to show that the general architecture can be applied to different wavelengths, optical configurations for different applications. So till this moment, we're restricting our discussion in visible light. But of course, since we're just building an optical camera, optical street camera, can be targeted, at short wave, right? So we just need to replace the camera from silicon to InGaAs. And my student Miao is working on information security. Right? So this one is basically a normalized intensity map of this flower pattern. So there's no signature. But if you switch to lifetime, then it's very obvious that you see we actually put different types of nanoparticles in one of the petals. So this, in our opinion, is safer compared to the intensity contrast. And so now we're trying to combine spectral and temporal information to further enhance the temperature sensing capability. So at 1 billion frames per second, we have an industrial collaboration with a company to bring the compressed ultrafast photography to ultraviolet. So this one is still, to our knowledge, the fastest UV camera, and we recently sent it to a synchrotron Soleil in France for I guess X-ray pulse characterization in synchrotron. So in trillion frames per second, I just want to share this. It's not very clear. Oh, now it's good. To basically show how can we do optical encoding at light speed. So we start by using a chirped pulse and associate the temporal information with different colors. And then we built this modified 4F pulse shaper so that the pulse are chirped and also shared in this way. So it can pass through a very big coded mask, and the second grading will bring everything back. So this means that if you look at each color, the encoding is different, and this will allow us to probe the dynamic scene at 1 trillion frames per second in one shot for analysis of materials science dynamics. So again, I won't go to the details, but I mean, here the first example is we image a laser-induced demagnetization, and with some ongoing work to extend this to image the optical switching. And also, we pushed the imaging speed all the way to 156.3 trillion frames per second. And we imaged a transient absorption of semiconductor. And, this number may actually, generate lots of question marks, right? So, I mean, what things can move, faster than the speed of light, right? But, if you really look at what's going on, it's basically you have the wavefront impinging in this way, right? So the photons is moving this way. But what you're looking at here is essentially a projected speed. So it's just like if you're swinging your laser pointer, right? So if you don't stand far away, then the imaging speed looks very low. But if you are standing on, let's say, on the moon or Mars, right? So this will still be much larger. But anyway, so I guess official answer is that, well, even if this looks like an event that's faster than light, but we don't really have information that transferred from point A to point B. So this is just you call it illusion, you call it the projection speed or whatever. So we're still fine. Okay, so Einstein's still right. Okay, so let me quickly summarize. I guess I'm running out of time. So today, I hope I just give you some concept that, computational imaging is pretty broad, right? But I guess encoding can be regarded as a very common strategy to overcome the limitation in existing optical or optoelectronic devices. And here, what we are doing is related to a specific imaging modality called streak imaging. So by combining encoding and streaking, we'll be able to retain X, Y, and T information in just a single shot. And the encoding in the context of streak imaging can usually do two things, two good things for us. The first one is it will help us to break the time continuity so that we can get a framing photography. And two is that, if there overlap between adjacent frames, the encoding can help us to, provide a barcode, if you want to think about it this way. So that, this prior information will help us to extract the information during the reconstruction. So this is a very generic scheme, and it can be embodied by many different imaging configurations. So here I talked about the framing photography and how it can be used for light matter interaction. And I also talked about the compressed photography for applications of material characterization, public health, biomedicine, and information security. So last, I'd like to acknowledge my group and also for the support. And I stop here. Well, thank you very much.
Yeah, this is amazing work. So you talked a lot about the encoding side of things. I was curious about the decoding side of things. So where do you see the biggest opportunities for computational algorithms on top of the optical systems you're developing?
Yeah, well, that's a very good question, and I don't know if I have a good answer for you. Okay, I mean, I'll try my best. In fact, I mean, this is one of the reasons why I'm here, right? So to acknowledge that, like even if we're trying our best from the optical engineering perspective, we just don't know how to do this decoding part properly, right? So that's why I called myself a user of some of the algorithms. So to your question, I would say like one opportunity or one thing that I would like to do is to say that, okay, I mean, now we're all trying to see some, small field of view, I mean, the sample is well prepared, and how to actually use, let's say, high-speed imaging in a real-world scenario, as I mean, many of your work has shown, right? So we think that if we can get, let's say, a million frames, a million pixels per frame, and let's say a million frames per second, that would be a major, in my opinion, major breakthrough here. So we actually are moving towards this direction. So we are collaborating with a company to commercialize this thing, and we're trying to add a telescope right in front of that, so that we can actually see some things far away. But I mean, what we know is that like even if we can take in the images, the reconstruction is just not nearly as good as like you guys work. So how to get there? Like if you were talking about the specific toolbox to use, I don't know. But I just know that if we can have a million frames per second at million pixels per frame, that'll be sweet. Right? And I guess another thing is that as I told you this morning, I think there's still barriers between areas, even though I think both of us can be regarded as researchers in computational imaging. So we just know that like if there can be some collaboration based on some joint database, that would be good, because I mean we have ability to generate lots of data, right? No matter if you just want to use them for training or to do reconstruction. At the same time, if we have the access to some of the latest work that we are doing, we would like to have the opportunity to learn, right? So I think the learning curve is there, but I mean, if the goal is that like we want to bridge, right, and trying to bring the advantage from both sides, so that this could give a quality change in the level of computational imaging capability. That would be good.
Yeah, good. Well, we'll chat more.
Sounds good.
Yeah, I was curious just about one thing, which is first of all, you unveiled an entirely new world. Very, very unfamiliar with this topic, but I think I heard at one point about some event cameras that rather than sort of like integrating each pixel, when a photon comes in, it's like a Geiger counter, right? It records this pixel receives this photon and then streams it out for us. And I was thinking that ultimately this should be the dream, right? That you capture the individual photons, but this is the best we can do now. Or...
Right. So that's a very good question, right? So I mean, getting into the single photon level sensitivity is definitely a dream, and this is also within our radar. With the event camera, what we think the limitation is that you kind of lose the capability to capture the grayscale information. So, no matter if you want to talk about SPAD or event camera, it's like, lots of times you're event driven, right? So if there's something there above the threshold, okay, there's a spike. So there's also, I guess, another very interesting device coming out nowadays. I think it's called the time pix sensor. So it's generated by a CERN project. But for that one, it can give you a very nice timestamp. At the same time, it retains the grayscale information. But the downside is that in terms of visible photons, it doesn't have the single photon sensitivity. So in order to use that, you have to combine that with a intensifier. But if that's the case, I mean, you can call your device having a single photon electron sensitivity instead of saying like it has a single photon sensitivity. We think that if we want to retain the ability to have the grayscale information capture with the single photon sensitivity, EMCCD is probably the way to go. So for example, I'm working with a few people in some quantum imaging. So there, we're trying to bridge the streak imaging with EMCCD, so single photon counting capability, to see if that we can capture everything. So back to your question, well, yes, the SPAD or anything that can retain, can give you a very precise timestamp is definitely advantageous. But here what we're trying to do is that we use the streak to provide the time sensing capability while retaining the advantages of some conventional high sensitivity sensors. So in this case, we want to bring in the high-speed imaging capability without losing its own niche. So I hope I answered your question.
I think you did. Maybe the one remaining confusion, if I may, is that so basically, if we capture single events, it's physically hard to also capture the intensity. That's basically what you're saying.
To my knowledge, yes, yeah. So